Hi, I'm Dan Roche. I'm a professor in the computer science department at the U.S. Naval Academy. And this is joint work with some colleagues at the University of Grenoble in France and some students there and at my institution. We've been working on this for a couple years, and I'm really excited to tell you about our work. So the basic problem that we're looking at is how to make sure that remotely stored data in the cloud or something hasn't been deleted or altered or tampered with. And the main mechanism for doing that is what's called an audit. And previous solutions have some kind of downside. Either their audits don't end up checking everything, so it can allow in small changes, or they require a much more expensive duplicated storage, and they're not transparent. And so what we did was, first of all, show that some of that trade-off is actually inherent between the audit time and the audit completeness and the storage size. And we found a different way of doing it that actually has good complete checks and transparent storage, but at the cost of having a slower cost for audits on the server time. And then we show in our implementation that actually that slow server time cost is quite a low linear time and is really practically beneficial compared to previous solutions. And when we're talking about this, there's a few images I'm going to use. The first is our client here, which is completely honest in our setting. The server is malicious, so we don't trust the server at all. That's the point of doing an audit. The data that we're storing, in this case, is going to be an image of some cheeses. And finally, when I have to talk about a hash digest, I'm going to use this picture of a hash brown. The basic operations that we always want are to be able to read a single block of data and to write, to like add some salami into this picture. These are complicated to get right in the light of the audits, but not what we're going to focus on because it's not really a point of distinction between what we did in prior work. These are always pretty good solutions nowadays. But the point of distinction is the audit. So with the audit, we want to have an interactive protocol to make sure that the data is still intact. And at level 0, you just trust the server to not delete anything. This is kind of a joke, but it's really what we currently get for big cloud computing companies like AWS. You just have to believe, based on their reputation, that they're not going to be deleting or altering your data. Maybe you're okay with that, but even if you are, there's new mechanisms called distributed storage networks like Filecoin, where your data is actually being stored by like blockchain miners across the world, and you really, really shouldn't trust them. So we need some more powerful audits. A basic audit that'll always work is just downloading the entirety of the data and checking it against a hash that you may have saved. And that works. And this is a complete audit. It's great, except of course it's quite slow. So it's going to have a really big communication size. It's not very efficient. So a better way is what's called provable data possession, or PDP. These methods have been studied since at least 2007. And the basic idea, although there's a lot of enhancements in the series of papers on this topic, is to randomly check a block of the database. And how do you do that is by having some kind of like a Merkle hash tree. And then you can repeat that a few times for a few different blocks. And when you do that, that ensures with high probability that most of the data is intact. That works, except that word most that I use is really important. So if you look at this picture, you might notice that something changed. I threw an onion in here. And so if you have a small change to the database, it's actually likely to be missed by a PDP audit. So if you have a big change, if you delete a lot of the data, it's going to be found by these checks. But if you have a small change, like adding an onion, that doesn't make the client very happy, but it'll be missed. So how can you avoid that is a different line of work called proofs of retrievability, or POR, also studied for about the last 14 years. And the idea here is usually that you duplicate, maybe using erasure codes or something, and shuffle and encrypt the data. Think of like ORAM type techniques. In fact, ORAMs were used in some of these papers. And what does that do is it allows us to do a PDP style audit where you just randomly check a few blocks. But now, because everything is encrypted and shuffled, losing a few of these blocks, as we could do with PDPs, is not going to affect the retrievability of the overall data because it's been duplicated. So the idea is to say, okay, we'll allow the fact that our audit may miss a few blocks, but that's okay because we're using this kind of duplicated storage. And this works, but now it's the problem is really this storage on the server. It's not transparent and it's really big. So it's going to be expensive, and it prevents the server from doing optimizations like deduplication, which is really important in practice, or to do its own, say, like database search, because everything is encrypted from the server's view. And so just as a comparison, in the previous work that we just talked about, there's always some kind of downside, usually between like the completeness of the audit or the size and transparency of the storage mechanism. And we first have a lower bound proof that you can't have it all. So literally these four attributes are somehow in conflict. There is no such system. We proved that there is no such system that can satisfy all of these. But our work, our new approach, finds kind of a different space on this landscape where what we're going to be sacrificing is the audit time, but not in terms of the client's work. So the client's work and the bandwidth for communication is still going to be low, but the server time for audit is going to be linear. And then we show that in practice, that linear time, server audit time is beneficial, is not too bad. The new strategy is roughly summarized as treating the data as a square matrix. It doesn't require modifying the data. You just treat the bytes as numerical values in a square matrix. And the idea of audits is to choose random linear combinations. So the client's going to do a random linear combination of the rows. The server is going to do a random linear combination of the columns. And then during an audit, the client just has to check kind of the random combination of linear combinations in two different ways to see that they're the same thing. The mathematical justification for why audits work actually goes back to some work from Freivalds in 1977, and it really boils down to this equation here. So if A is what the client thinks should be stored and B is what the server is actually storing, then we can multiply by these random vectors on the right and left. And there's a proof that if you get equality over a large enough field with these matrix vector products, then that proves that with high probability, the two matrices, what the client thinks is stored and what the server actually stores, are the same. So visually, what happens is that during initialization time, when the client has access to the complete data, they choose a random vector and compute this U transpose A. Now, these are both going to be secrets which the client saves. So when the data is then offloaded to the server, now during an audit, the client doesn't have the data anymore. They choose a random vector X, send that to the server who computes their own linear combination of the columns. So that's this BX over here, and sends that back to the client who now computes two dot products to check. And if they match up, then that proves that the server stored actually still stores all the data intact. We implemented this and tested it using Google Cloud Compute, using actually relatively low-powered virtual machines. And what we compared with is a number of things, but we compared with the MD5 sum checksum algorithm. So this is actually a now insecure cryptographic checksum, but it's used for some kind of similar integrity checks, and you might be familiar with running MD5 sum when you download some untrusted file from the internet. And what we show is that the bad thing about our work is the slow server audit time. And we see that it's not that bad. It's actually an order of magnitude faster than just doing an MD5 sum. And the client time for audits is extremely low, less than a fraction of a second, even up to a very large 1 terabyte size file. The downside, however, with that is that it depends on client secrets. So the client has to have these two secret vectors that it saves that can never be revealed. And to get around this and allow anyone to perform an audit, what we use is something like something between a cryptographic hash and a linearly homomorphic encryption function, which I'll call H of alpha, which we actually just use as exponentiation in an elliptic curve group. And that allows us to take this private audit where we have these two secrets that the client has to store, and turn that into a public audit where instead we're going to publish the component-wise hash of those two secrets, and the linear homomorphic properties allow us to do the same check. And what's important to recognize here is that the server's computation, so this is the expensive thing for us, is really exactly the same. The server doesn't have to do anything with elliptic curves. The only difference is that the size of the finite field that you're working over, the size of the modulus, has to be a little bit larger for the public audit, so that slows things down a bit, but not too much because the server still isn't kind of doing any hard crypto operations. And here's the experimental comparison for public verifiable audits, what we see is that the server's computation time is a bit slower, but still even a little bit faster than MD5 sum. The client's computation time, or the auditor, is significantly slower, but it's still fast. So it's still something roughly near 10 seconds for a 1 terabyte database to check those two dot products. And so that's what we have in summary. We have kind of the best of both worlds in terms of PDPs and PORs. We get the efficient, transparent storage of PDPs with the complete audit retrievability guarantees of PORs. And the downside is we have a slow server time for audits, but we still have small bandwidth. And in practice, this slow server time, when we measured it, it's very inexpensive. It's something like 10 cents and 5 minutes on current technology to do a 1 terabyte size audit. Compare that to the cost of actually having this duplicated storage in previous POR solutions. That's going to be much more expensive. So that's it for me. Here's my 2 favorite clients, and thanks for your attention. I would love to chat about this more with any of you at any point in time.